Hello, everyone, and welcome to today's webinar. My name is Jason Walls from QA Cafe.
And I'm John Blackford from ARRIS.
Together, we are the co-directors of the Broadband User Services Work Area at the Broadband Forum, and that is the group that has developed and maintained Tier 69 for about 15 years now. We're glad you could join us and have us talk to you about the User Services Platform, or TR369, that was published earlier this year. USP is kind of the next evolution of Tier 69 that is designed to meet some of the most pressing needs of the connected home now and in the future. Here's what we hope to cover today. The first 2 points are really the why of USP. We'll examine what got us to where we are now and go over the high-level use cases that USP enables that go beyond the design of Tier 69. While we go through these use cases, we'll show you some of the specific parts of the technology that make this possible. I'll also show you some examples of USP messages in our CDRouter logs so you can get a basic idea of the differences. And then lastly, we'll talk about the testing plan for USP and how to start building or developing requirements for your own implementations. At the end, we will go into questions. Some of you gave us some questions ahead of time through our questionnaire. We are using GoToWebinar for this, and if you've never used it before, you can type your questions in the question box in the lower right-hand corner of your GoToWebinar control panel, and we'll get to those questions at the end. Also, if you have trouble seeing some of our examples, you can use the zoom feature at the top of the GoToWebinar screen to get a closer look. So let's take a trip back in time for a moment. The year was 2004. Mark Zuckerberg had just launched the original Facebook from his dorm room at university. In the US, the Red Sox were on track to break an 86-year championship curse in baseball, which is very dear to me. And the UEFA Europe football tournament saw a surprising upset when Greece ended up taking the trophy. But behind all this, service providers everywhere were having a very real problem with broadband gateways, which had already become pretty complex devices and a regular part of their deployments. Onboarding these devices was getting tedious and expensive, mostly relying on truck rolls or user setup via CD-ROMs or UPnP. There was a real need for a standardized system for lifecycle and firmware management, for maintenance, for monitoring, and provisioning new services. And it was back then that the Broadband Forum released the CPE WAN management protocol that you all know and love more commonly as TR69. I'm going to assume a bit from your responses to the survey we gave that everyone is at least somewhat familiar with TR69's architecture. The key things to point out is that it's made for customer equipment to connect to a single auto configuration server, which is often integrated into OSS and BSS systems. And then underlying TR69 is what's known as a data model, which is a description of the objects and their parameters that represent functions on end devices like network interfaces, network applications, and statistics. So over time, TR69 expanded to cover more kinds of devices by adding new features and expanding the data model. These included set-top boxes and VoIP devices and Wi-Fi access points and a lot more. Then around 2010, the cable industry began using TR69, specifically the Device 2 data model, to manage some of their more advanced gateways and Wi-Fi capabilities. Since then, of course, the connected device world has exploded. The average home has more than just a laptop and a home computer, but tablets, phones, set-top boxes, TVs, smart home devices, all that stuff, all connected through their broadband link and communicating with third-party services. This brings us to why it was time to evolve TR69. The connected world now has a much bigger scope, not only in terms of new kinds of devices and interfaces, but virtualized services, third-party interactions, and a real desire for end-user control that creates a seamless connected experience, just as users have now with their mobile connectivity. But it's also a question of scale. There's now an order of magnitude or several orders of magnitude more devices and more connections surrounding the connected user. And consumer electronics that are now network aware are forced to commit to some longer product life cycles that they're not used to for upgradability. And this explosion really creates a problem where more telemetry is needed, but also an opportunity for it to be used to fuel really advanced AI and machine learning applications. And this expansion of scope and scale really means the stakes are bigger too. I mentioned the upgrade lifecycle, and at its heart, this is a security issue. Connected devices really need to be able to patch vulnerable software. And with telemetry in the smart home, there's some serious privacy and data security concerns. And lastly, the question of who owns, who can access, and who is responsible for which connected devices is an ongoing conundrum. So this is the big picture of the components and architecture of USP. I'm not going to have you stare at it too long right now because it's a lot of stuff, but we're going to keep coming back to this slide. The key thing that I want you to keep in mind is this. The user services platform is a network of controllers and agents that manipulate service elements using the robust data model defined in Device 2 to allow for migration and coexistence with TR69. Now, as John goes through several USP use cases, we'll come back to this diagram and sort of point at exactly which of USP's technologies enable those use cases. John?
Thank you, Jason. So if we go to the first use case here, we're looking at explosion of the managed devices inside the house. So the problem being that, between the new Wi-Fi mesh solutions that have been coming out over the last few years, and as well as the smart home solutions that keep becoming more prevalent, we're looking at an order of magnitude more devices in the connected home, all of which need to be remotely controlled and maintained. So it's not just the gateway and a few set-top boxes anymore. We're adding now, a couple of Wi-Fi extenders, maybe a dozen or so smart home devices spread between light bulbs, door locks, cameras, smart TVs, etc. So instead of managing 2 or 3 devices for each subscriber, we're now looking at 12 to 15, even more per subscriber. So if you multiply that by the number of subscribers that a service provider or an operator has in their network, you're starting to see, a definite order of magnitude. Your 10 million deployment before is going to easily turn into 100 million or more devices that are under management. And so when you start looking at that order of magnitude, a lot of concern starts to come around network bandwidth consumption and usage. So the solution here is first off, having an always-on communication channel helps reduce the number of messages sent across the network. As we see in TR69 CDMP, every time a management entity wants to communicate with a device in the home, it has to establish a communications path, and that includes several messages that happen. But with an always-on communications channel, as the device comes online, that's when the communications path is established, and then after that, each request is sent on its own. It doesn't have to do some kind of pre-work to get the session started. So that definitely saves on the number of messages being sent across the network. And then we also have binary data encoding and relative path usage, which help to reduce the size of the messages that we're sending across the network. So from a binary data perspective, we're looking at a smaller data footprint than, say, an XML, SOAP XML footprint. That reduces the size there. But we're also in USP, we utilize what we call relative path usage. So that means that if you were to do a get parameter values in TR69, you would ask for a fairly long path, and then that path gets repeated in the response for every parameter that comes back. But in USP, we don't continually repeat that path. We give the path back once, and then everything else is relative to that path. So that cuts down on a lot of characters that are sent across, and then the size of that message. So the key USP features here are the always-on communications mechanism, as well as the network traffic efficiency. So if we go to the next slide, this is what Jason was kind of talking about, how we're going to come back to this big picture and kind of show for each use case how the big picture ties into that. So on the left-hand side here, we have the always-on communications channel. So this is basically in between any of the controllers and the USP agent. We have this pre-built communications channel that gets established when the device comes online, such that if a controller wants to send a message or a request down to get some information or set some information, that communication channel doesn't have to be established at that point in time. And then on the right-hand side, we see the efficient messages and robust responses. So that's where the protocol, the USP Message proto file comes in, which is actually Google protocol buffers. So this allows us to send a binary data encoding across the line. And also, we see the different messages up here basically are CRUD-based, kind of REST-oriented messages where you have create, read, update, delete, which are in USP gets, sets, adds, and deletes. There's a couple other messages we have here to round out what we would need and keep it kind of similar in nature to how Tier 69 did things, where we have an operate, where we can execute data model commands on the device, and then we also have a notify for event processing. All right, so Jason, if we go to the next slide. So next slide here, we have use case around application-based end user management and control. So the basic problem here is that, if it's in the house, we want an app to manage it. We're becoming a society that is more kind of driven towards our tablets and our smartphones to help us control the home network. And so, the Wi-Fi in your home network, you want an app that helps you, figure out what's going on with your Wi-Fi in your home network, how efficient it is, what your speeds are that you're getting, what devices are connected, and how much data they're using. As far as your smart home devices, your lights and your door locks and your cameras, you want an app to be able to kind of look at them and see their statuses and even control them. And the same goes for your TV and your video that you look at. You want to be able to see your video feed on not only your TV, but your smart devices as well. So we not only want all of those apps, but we want them to be very responsive, and we want them to display relevant information independent of whatever devices we might be using. So basically, we want the network to work for us. We don't want to work for the network. So the solution here is that we have, always-on communications, again, as we mentioned in the last use case. That helps lead to a more responsive experience because you don't have to wait for that communication session to be nailed up before you start asking devices for information. But that's kind of just the first step here. With USP, we also have a co-app message transfer protocol, which is a UDP-based mechanism that actually has some fairly fast communications that it enables. And so it's really good for in the home network, and it helps to create a seamless experience when you're using the application, because it just provides you, almost instantaneous responses back from the devices. We also want to have, robust and forgiving messaging, because we're going to have different devices out there. They're going to have different data models that they support. There's always going to be, extensions that a device implements so that it makes it, a little bit better for its environment that it wants to work in. And so we need a way for our messaging between the management endpoint and the device to actually be forgiving and not kind of fail whenever something might go wrong. We want to be able to get back as much data as possible and then realize what data isn't available. And so some of the key features in here are, flexible deployments, robust responses, multi-stakeholder architecture. And if we look at the big picture, we'll see how this all ties together. In the multi-stakeholder architecture up on the top left, this is basically talking about how you can actually have multiple controllers. It's not just your operator and your ACS concept anymore. You now can expand into any number of service providers having access to devices in the house at any given time. Again, on the efficient messages and robust responses, that gets into our USP messaging box there on the right-hand side, where we have very forgiving messages that don't fail whenever one thing goes wrong. And then in the bottom right, we have flexible deployment support, which is really talking about how in USP there are multiple message transfer protocols that are available, and each one of them has their own, special needs or special usage. CoAP, for example, is very good when you're doing communications inside the home, as it is UDP based. But Stomp and WebSockets would be something more needed when the smart device, the tablet or the phone goes outside of the home and still wants to communicate with the devices inside the home. So on to the next use case, security and privacy. So basically, we kind of live in a new world where security and privacy is very, very important. There's always, someone out there looking to take advantage of any kind of attack vector that might exist into the home network. We've seen it, several times in the past about, the Internet of Things and those devices, as they're, usually smaller and easier targets to be attacked because they don't have as much security. So that's definitely one of the things that we're looking to help close here. We need to be more secure than ever because we need to protect, privacy. So we need to provide these tools that help implementations do so. So some of the solutions that we have in place as part of USP is that, we're definitely encrypting the communications channel by TLS and DTLS. That's always the first approach, but we don't stop there. We also have an end-to-end security mechanism as part of USP, and this allows us to ensure that messages that are being sent between a controller and an agent are protected end-to-end because there's a encryption mechanism established between those two endpoints. And so any proxy or man-in-the-middle kind of solution that might be in between those two endpoints isn't going to be able to read that communications. Regular firmware upgrades are another big part of what we've established in USP, and that helps to close those attack vectors before they become a true problem. We also have strict access control. So this ensures that rogue controllers can't reach out into a device and retrieve data that they're not allowed to access. And it also helps to kind of separate the different service providers and make sure that they only are accessing the data that they're supposed to access, or that you've granted them access to as a subscriber. So for example, if you have your high-speed internet provider, they're accessing your home network, and their responsibility is to make sure your home network is working, but that's more from a networking perspective, not necessarily being able to read data off of certain devices. For example, your home security system may want to be able to read, pull into your camera feeds and figure out when doors were open and closed, but that's not necessarily something that your high-speed internet service provider should be able to see. So USP does provide you the way to put those access controls in place such that one service provider can read data and the other can't. So the USP key features here are the MTP encryption, the end-to-end security, and the firmware upgrades and access control. So if we look at it in the big picture here, at the top and the bottom and directly in the middle, you'll see the firmware upgrades and the lifecycle management approach here. So this is definitely a two-phase or a two-part solution, because you have your controller that's kind of defining what your application policy engine is around firmware upgrades, when to apply them, what devices they need to be pushed to, and at what point in time do they need to be pushed. Do they get pushed immediately, or do they get more scheduled into a maintenance window? But you also have the USP agent side or the device side of firmware upgrades, which is the one actually responsible for applying that firmware upgrade when it happens. On the left-hand side, you have your privacy and access control mechanisms. This ties very much into your service elements as it's tied into which portions of the data model need to be given access control to different controllers. On the right-hand side, you have your end-to-end security. This is where the USP Record comes in, and the optional session context with TLS. And then at the bottom right, again, the MTP layer encryption where we have TLS or DTLS, depending on which message transfer protocol is being used. So if we go on to the next use case here, we'll talk about mass telemetry. So operators are, they're looking to understand the quality of experience that they're providing to their subscribers. It costs more for them to gain a new subscriber than it does for them to keep an existing subscriber. So they're constantly looking at how do we improve that quality of experience that we're trying to deliver, and mass telemetry is definitely one of the ways that is being embraced recently. Being able to collect data from all the devices under management and pull that back in to do some analysis on. So the solution here with USP is, USP is definitely a more efficient protocol than previous versions of TR69 and some other management protocols as well. So that does help in the data collection, but we also in USP offer kind of an out-of-band or a decoupled mechanism for data collection that doesn't pollute the remote management channel. And it's known as HTTP bulk data collection. So it's basically a way where you can tell the device that this is a set of data that you want to collect. You can tell it how often for it to collect and where to actually send that data. And that kind of it creates a side channel, so to speak, such that it doesn't keep that data on the management channel, and you can keep that dedicated to just management information. So once that data has been collected, then the operators have the opportunity to analyze that using big data analysis tools and machine learning solutions. So to see how this fits into the big picture, we have, again, your multi-stakeholder architecture, so different controllers. Each one of those could set up their own mass telemetry solution, whether it be using the actual USP messaging or the out-of-band bulk data collection mechanism, which leads to kind of the middle arrow there, which is showing how the out-of-band bulk data collection happens, not over the message transfer protocols, but just off to the side. And then on the bottom left, a standardized device 2 data model. That means that everybody is able to kind of look at the concept of what the data is on the device in a similar fashion. And again, on the right-hand side, the efficient messaging and robust responses, that's if you want to do your mass telemetry collection over the actual USP messaging. All right, so down to the next use case here, which is a greenfield versus brownfield. So any new solution has to consider both greenfield solutions or greenfield environments where you're dealing with brand new environments, as well as brownfield where you're looking at more existing environments with specific constraints. And so one of the key design goals of USP was to keep the data model consistent with TR69, because mapping the data model to underlying libraries and system calls is one of the biggest investments for a CPU when developing a management solution. This is why utilizing the device 2 root data model was of key importance, as it allows current CPE to reuse existing investments and speed up their time to market. But at the same time, utilization of the device 2 root data model allows for backwards compatibility, and that plays into existing ACS vendors and integrations that they may have and gives them a faster path to adoption. Because that definitely means that CDRP deployments aren't going to go away, and we're not going to be ignoring them. Tier 69 enabled devices are going to be around for quite a few years to come still. So we definitely have to consider coexistence between USP and CDRP. It's a very important concept, and it's going to have to be dealt with. So looking at the big picture here, a little bit different than the previous big pictures because we just want to focus in on the actual communications between the controller or ACS and the device itself. So at the top left, we see your multi-stakeholders, meaning that you can have both a controller and a TR69 communicating to the same device. Then you have your standardized device to data model. That basically is showing how, underneath the covers of the device, you have this mapping between your device to data model and your underlying concepts, libraries, and so forth, and how that just maps into different levels of protocols. So as you can kind of see, you have both a USP endpoint and a CDRP endpoint, both coming into your instantiated data model there for the communications. Privacy and access control from a USP's perspective is also going to come in hand here, as you may want to have different portions of the data model exposed to USP as opposed to TR69. And then the last arrow that we're showing here is the coexistence with TR69. So it's just kind of showing how both of them can coexist at the same time, both talking to the device. And on that note, I'll turn it over to Jason for the next slide.
All right, thanks, John. So let's review all that a little bit and go into a little explanation of the key aspects of USP that enable those use cases. The first is that the message set, or the RPCs, if we were talking about tier 69, have been both streamlined and enhanced. There's mechanisms for performing RESTful operations like creation and deletion, or for updating an object through set. However, the managed connected world needs more than just RESTful operations, and so USP has an operate message that allows controllers to call specific synchronous and asynchronous functions. These functions are now defined in the device to data model, like firmware download, which makes for easy expandability later. So we no longer have to make a new version of the entire protocol every time we want to add a new RPC, and the operations can be object specific. There's also a notify message, which allows for events to be transmitted from an agent to a controller, again, extensible through the data model. And lastly, the addressing of an object or a parameter in the data model can now be done via search expressions or wildcards. The responses to messages in USP are much more efficient and forgiving. Rather than asking for a set of information and just getting an error, USP will still give you the information you want while telling you which things didn't work. You can also have the messages that change state, like add, set, and delete. They'll let these successful changes be made, even if some of the changes fail, if that's what you want to do. But most important here is the fact that the message footprint and session overhead have been drastically reduced using always-on connections, protocol buffers, and the relative path usage. And I'm just going to cut away really quick to this to show you what this looks like. So we have a CDRouter log here of a test that was run. And so CDRouter is actually showing you the reconstructed message rather than the message that's sent on the wire. But this is what a USP message would look like. So you can see the get here from the controller, which is just asking for all of the information under device.localagent.controller, just like a partial path in tier 69. And then you see the response. You can see the USP record here. And then the response shows you the resolved path, and then the parameters underneath. You can see that it's just giving you the parameters rather than spelling out the entire path of each one. But I want to show you the difference between, so again, this is the reconstructed message on the wire. If we go over to an actual USP capture on CloudShark, on the wire you'll see, if we follow stream here, you'll see the actual, this is the binary encoded data, which is much smaller than you would see if you were to do this with TR69 or even if you were doing it with JSON data. It's significantly smaller on the wire. So I want to also talk about the transport bindings, because this design is a big departure from almost any other protocol that's out there. TR69, as you know, is heavily bound to HTTP. So even building the XMPP connection request mechanism had to be done out of band. In USP, the lines between protocol and transport, which we call message transfer protocols, or MTPs, to not confuse it with the actual OSI transport, that line is very clearly defined. And this not only allows for future expansion, but it also ensures that the protocol will operate the same way, regardless of the use case, whether it's traditional management or control points that are moving across networks, or when you're using USP on constrained devices. USP's method for defining and delivering events via the notify message is also a unique feature. There are core events built into the notify message, but beyond that, the events can be defined in the device to data model, allowing for object-specific notifications that are easily extensible. This works by controllers subscribing to a certain notification by using the add message to create an instance of a subscription object. And there's references to the objects and parameters that are the subject of the notification. And that can even be a search expression to cover multiple objects. And the last, but maybe most important feature, like John was talking about, is the security and access control. The USP record layer allows for an optional session context, which can be secured via TLS, and that's at the application layer, which means it's secured from end to end. This is important because internet networking requires crossing certain points that can be a single point of failure for man-in-the-middle or other attacks. And secondly, the multi-controller architecture is secured, and privacy is enabled by that role-based access control we were talking about. That is, only certain controllers can see or do certain things. And that access control is actually easily managed via the data model. All right, so where is USP now, and where is it headed? For testing, QA Cafe has already developed test suites and automation for USP that are based on the current Plugfest test plans, as well as the initial set of broadband form conformance tests. This includes support for implementations using any of the message transfer protocols. So we'll support any device that's implementing USP using Stomp or WebSockets or CoAP. John, do you want to talk about ECO and the plan for testing going forward?
Yeah, sure. From the ARRIS side, we've created both a USP controller and the USP agent. The USP controller is called ECO Control, and our USP agent is called ECO Envoy. Both of these components are part of our ECO software, our software suite called ECO Service Management. From an ECO Envoy perspective, that's the one we kind of use for testing with the CDRouter USP testing module. So, that helped validate the testing of the CDRouter module. It also helped validate the ECO Envoy implementation. Being so early to market with, USP is 6 months since it's been published. So being so early to market, there's not a whole lot of deployments out there to validate against. So testing with or against the CDRouter definitely helped our implementation. And it also helped the USP specification testing because we've, as we tested, we came out and found several kind of small issues that we've been targeting in broadband forum as core genom fixes to the USP specification. So if we go to, what other testing is happening and what other items are happening around interop and compliance. So we've already had 2 Plugfests to date. which are Plugfest or group testing events with multiple participants, on both sides, both the controllers and the agents, where we all just get together and we test against each other to see how interoperable we are. So we, in the two Plugfests, both ARRIS and QA Cafe have been involved in that, as have a number of other vendors. The next Plugfest is being planned for April of next year. Your participation is welcome. If you've got a deployment that you want to, implementation that you want to try to test interoperability with other people, that's where we do it. The Broadband Forum is also developing a certification test plan that'll look at conformance, interoperability, and functional testing. And the Broadband Forum is also looking at a certification program for around USP. And so we'll have more details about those tests, about that test plan and that program in the first half of 2019.
Okay. All right. So what do you do if you want to start implementing USP? The full specification defined in Broadband Forum TR 369 is actually published on the web at usp.technology. And I'll actually go there right now and show you what that looks like. It's at this website right here. And if you click on specification, you will find the definitions for architecture, discovery, messages, the entire protocol. And if you do want a PDF version of it, you can find it here too. And then the US data model, the USP data model is actually generated from the same base as the Tier 69 Device 2 data model, with some changes for operations, events, and the objects that are specific to USP. But you can find that on the web here at USP-datamodels- at broadbandforum.org. And I'll take a look at some of these. This is laid out just like the CDMP one is. So you can scroll down here. You can find the most recent version. So support for USP it's the earliest version of Device 2 that supports USP is Device 2.12. And it's as familiar as you imagine. That shows all of the objects and interfaces and everything that you need. And I'm going to jump over here to show you a USP specific one. So this is device.localagent. Local agent is a USP specific object, and the subscription object, which is used to have the controller subscribe to certain notifications and events. And so all of the the normative requirements for how that's supposed to work is all within the object and within the parameters. So if you're looking to implement that, then you want to go here. The other thing to look at is the protocol buffers schema definitions. So you can find those in the spec if you go to the encoding, the page about encoding, but you can also find them directly on GitHub at this link right here. So the protocol buffers are basically they're schemas, so that allows both endpoints to understand and communicate with each other with a very small amount of overhead and some really easy coding steps. And then lastly, automating the testing of your implementations is obviously going to be critical to doing it right. So for very good reasons, some very good reasons, USP is pretty complex. Some of you on the call already have the CDRouter test platform. And for you, it's as simple as getting a hold of the USP add-on for CDRouter. And those of you new to CDRouter, we'd love to follow up with you on how you could be cutting the time and resources for development and deployment of any connected device by tenfold. So that was a lot of information, since it is a pretty dense topic. We'll be making this webinar available as a video online, which we'll send out to everybody after. But now we'd like to open the floor to questions. You can type your questions into the question box in the lower right-hand corner of your GoToWebinar control panel, and we'll try to address them as we come. We do have a few questions from, like I said, from the survey before, so let's get to those. And there is a question about migration and for which types of products are going to be supported. We've expanded so because it's using the Device 2 data model, we've also expanded the service data models to support USP2. as well. So if you're building a set-top box or if you're building a VoIP device, you'll be able to implement the service data models using USP as well. This is a good one. Okay, so what's the difference between the USP Record and the USP Message? The reason why there's 2 layers to that is for a couple of reasons. One was decisions we were making about what parts of the header should be encrypted, and what was the minimum set of information that that something that was maybe acting as a proxy needed to know. So that's why that stuff was sort of ripped out and put into the USP Record. But the other reason the record exists is to provide that end-to-end communications channel. So if you end up wanting to have that end-to-end security that is locked down at the application layer, the USP records are the mechanism by which they do that. And the USP message is what actually contains the RPC that is trying to be activated. So the difference would be is like the USP record says, who is this from and who is it going to, and this is how it's secured, and this is what you need to know in order to understand the message, and then the message contains the actual RPC. Okay, so here's a really good question. Is USP designed to run on IoT devices themselves? Yes and no. It really depends on, there are some IoT devices out there that are still going to be way too lightweight, even for USP. But it really is designed, it really can easily enable something like a smart hub, right? And we have a kind of a more advanced proxy mechanism, which we didn't go into here, more advanced than it is in TR69, that allows you to sort of replicate the device to data model under a tree that helps you describe other devices that are attached that might be running over different protocols. So yeah, that in your question, you're specifically asking about that proxy. Absolutely. So there's this proxy device table right here. The USP data model has sort of changed the data model schema a little bit to introduce the idea of a mount point. So what you can actually do with the proxy device table is use the same objects and parameters that you could from the device to data model to represent devices that might not be that aren't exactly on the same device that the agent is on. But in addition to that, there's also plans in place for a message transfer protocol proxy. So like if you have something that can handle USP, but it's only talking CoAP, there's a project in place at the Broadband Forum now for a message transfer protocol proxy such that device could talk to the gateway, and then the gateway will translate it into another message transfer protocol and send the message on.
Yeah, and Jason, that kind of also leads into what we're going to be showing at Broadband World Forum next week, where we have Greenwave there with their gateway that has a Zigbee embedded controller inside of it and a Zigbee light bulb, and it's going to be talking to the ARRIS controller, USP controller, to do manipulation of that light bulb return status, turn it on and off. All that information is actually being driven through the proxy device table that Jason's showing here.
Does USP allow the agent to be managed by one controller and data collect to another controller? Yes, absolutely. That is kind of a fundamental part of that use case, and it's based on the permission schemes. And even if you're going to be using the out-of-band mechanism, the permission scheme will lock that down. Okay. I'm glad that somebody asked this. In the architecture, it looks like we're saying that you are going to have 2 TLS tunnels nested. That's not necessarily the case. The design we have, the reason why this session context is optional, in the specification, we require that you use at least one of these things. So if you're satisfied with things being secured at the message transport layer over TLS or DTLS, then that's fine. It's also the session context is for if you don't have that, or if you really are trying to lock stuff down because you know something's going through a secondary system or a proxy. So it is a little confusing. It looks like you're supposed to always use both, but no, you just need to use at least one of these. And yes, we do envision USP and CDMP coexisting on the same device. That was, I think, this use case here. It's so, for example, there's a lot of people who are building sort of third-party managed Wi-Fi solutions, right? So if you're managing other stuff in the gateway via Tier 69, and you have another service that you want to use USP to manage Wi-Fi or some other aspect, then you absolutely can do that. And again, the permission scheme is what helps handle all that. There was a question about doing stuff from behind the net or the firewall, and that is kind of really why you can't just jump on a straight up REST situation when it comes to managing these kinds of things. And it's also the reason why we had this whole three different MTPs, right? So Stomp is a message transfer protocol, and it's like a message broker based protocol, a lot like MQTT, where it's connecting, or like XMPP, where it's connecting to a chat server to enable the controller and the agent to talk to each other across network boundaries and across firewalls and across network address translation. Oh, I do have one more question here that we'll do. Can you combine different MTPs for different functionalities? I don't remember. John, you might want to take that one. So the question is if we can use CoAP for telemetry and WebSockets for management. I don't remember what we said about having one agent using two different MTPs. Do you remember what we?
Yeah. An agent could certainly use multiple MTPs. I could definitely see an agent using CoAP inside the house for controllers that are subscriber controlled. So on tablets or smartphones, while also supporting either a WebSocket or a Stomp MTP for communications to external service providers. So yeah, I definitely would be able to have multiple MTPs there.